Hi, everyone. Welcome to the videos for Lecture 12 of Privacy in Machine Learning and Statistics. So last time, we introduced the problem of empirical risk minimization for a decomposable loss function. And we saw a generic algorithm based on exponential sampling. That algorithm was not always efficient, and even in the best case is just known to be polynomial time and not necessarily practical to run. Today, we'll see a class of algorithms based on the idea called gradient descent that sort of generically yield efficient algorithms, and they're actually generally pretty practical to run, even differentially privately. And they are essentially the state of the art, at least for the kind of a generic class of optimization problems. Okay, so what's going on? We've got our input is a function L that's defined on some set C and returns a real value. So this would be like L here. We're given the set C. It's a subset of R to the D. In this case, D is 1, but in general, we want to work with high-dimensional problems. And the only thing we're going to need from C is that it's some set onto which we can project reasonably efficiently. So projection is easy. And recall that projection is the following function. It's given an input X, not necessarily in C. I find the minimizer of I find the closest point in C to X. Okay, so like, given if this is my set C and here's my point X, then I should be able to sort of map it at X to the closest point in C, or a closest point in C. And this is pretty easy. For example, when C is the unit ball, or the hypercube, like -1, 1, the cube, -1, 1 to the D, or just everything, in R to the D. And there are lots of other examples where projection is relatively easy. Okay, and our desired output, so we're all on the same page, is to find a value W hat such that the loss of W hat is about the smallest we can get for inputs in C, and we want this W hat to also be in C. Okay, so the idea of gradient descent is you start with some arbitrary point W0, W0 that's in C. And what you do is you compute the gradient at W0. So that's like a linear function that lower bound. You should think of that as sort of the linear finding the coefficients of a linear function that lower bounds L in a neighborhood of W0. Okay, so let's assume that L is differentiable for simplicity. And then we're going to take a step in the direction of steepest descent of the function, so the direction opposite to the gradient. Okay, so the gradient in this case points to the right, so we're going to take a step to the left. And then again, we take another step to the left, and then maybe another one. And then, at this point, we've passed the local minimum, and our gradient is actually pointing us back the other way. And so our algorithm would sort of bounce back and forth around this local minimum. Okay, so we'd get sort of a sequence of estimators, W1, W2, et cetera. So if we want to take into account the constraint set C that limits potentially the sets of outputs we can find, then in addition to taking this step in the direction of the gradient, we'll also project back onto the set C to make sure that at each step, our estimate is like a valid estimate. Valid meaning in the set C. So what we get is the following algorithm. So it's, I'll call it PGD, which is short for projected gradient descent. So on inputs L and C, and a number eta, where eta is called the learning rate, or it's just some measure of how big our learning rate, or sometimes it's also called step size. So what do? We'll first start out with some arbitrary point in C. And then at each step, we'll do the following. Sorry. So the first thing we'll do, we'll compute the gradient of our loss function L at our current estimate, Wt minus 1. Okay. And in general, this can be a subgradient, for example, for convex functions. So any valid subgradient is okay. Okay, but we won't dwell on that. And then what we're going to do is we're going to update our estimator as follows. So we'll set u sub t to be our old estimate plus a step in a direction of opposite to the direction of the gradient. So that's the direction in which the function decreases most quickly. And that the size of that step will be multiplied by this this length, this multiplier eta called the learning rate, which we'll have to set appropriately based on sort of a bunch of parameters of the problem. We'll talk about that later. And then we get, so this gives us a value ut, and we get our actual next estimate by projecting ut, if necessary, back onto the set C. Okay, so the picture you should have in mind, here's our set C. Here's our current estimate, Wt minus 1, and somewhere out there, there's a true optimum, best point W star. And so what we're going to do is take a direction, let's say the derivative points, the gradient points in this direction. Then what we'd actually do is take a step here to get to u sub t, and then project back onto the set C to get our estimate, our next estimate Wt. Okay, and then and so on and so forth. So then we sort of continue in this way by computing the gradient, taking a step, projecting back if necessary, and so on. And then finally, what we do is our final return value. This is the final return value is some function of the iterates we've seen along as we're running the algorithm. Depending on how you set the step size eta, the best thing may be to output the last thing you see. Today, we're going to analyze a relatively straightforward variation where what we do is we actually output the average of all of the iterates we've seen. Okay, this is not the only option, but this is a simple one. So this is the algorithm we're going to analyze today. Okay, so this is a very sort of general purpose, framework for designing algorithms. You can consider doing the updates in different ways. You can consider doing the computation of W in various different ways, of W, your final W hat in various different ways. But they all the variations on gradient descent have this basic flavor. Okay, so what's the running time of this algorithm? Well, we've got t steps, and at each step we've got to compute the gradient. Well, we're manipulating vectors of length d. We're going to compute the gradient of that we take the time to compute the gradient of L. And we need the time to compute the projection. Now, we're going to be interested in what's called the decomposable case. So recall a loss function is decomposable if it can be written as an average over a data set of some small loss function applied to each data point. So this is the type of loss function you should have in mind. We saw lots of examples last time. So for those functions, what this really looks like is that you've got the time you spend at each step is really n operations for each, and for each one you're computing the gradient of a little loss function, and then you do some work to average those, right? Plus the time to project. And one of the things we'll see today is sort of how to deal with getting this, improving this factor of n with an idea called stochastic gradient descent. Okay, so that's our running time. And that's at least reasonable if the number of iterations we take is not too big and if our data set size is not too huge. Then this is actually already as it is a pretty good algorithm. The question that we're going to put off for now is how quickly this actually converges to some good value that we want to get, either a global minimizer for the function, that would be ideal, or a local minimizer if the function is not convex. So we're going to talk about that in part 2, and we're going to focus on the case of convex functions where we can actually argue that this procedure converges to a global minimizer. But in practice, this is the same procedure is often used for non-convex functions. It often converges to local minima instead of the global one, and that's fine. Okay, like in this example up here, this process is going to converge to a local minimizer. So the great thing about gradient descent is it's very robust to variations on exactly how you do things. In particular, we can use, instead of getting the exact gradient at each step, the algorithm continues to work pretty well in most settings if we use estimates of the gradient. And these estimates could be random in one of several ways. Okay, so for example, if our concern is getting an algorithm that's differentially private, we might want to add noise to the gradients. So one way to get a differentially private algorithm is to take our gradient that we computed at each step and add noise, add normal noise to each component of the gradient. So this remember, this is just shorthand for IID Gaussians in each component with variance sigma squared. Okay, and notice that if we, the advantage of this process is that if I look at the expectation of this G tilde, that's going to be exactly GT, the gradient we want, right? Regardless of the previous sequence. So or condition for every previous for every sequence of queries up to that point. W0, W1, T minus 1. Okay. So it's an unbiased estimator of the gradient, even conditioned on everything that we've seen so far. Another type of estimate we might want to use is for efficiency. So there, what we might want to do is what's called a stochastic update, or stochastic gradient descent. So there we could take our estimator for the gradient to be the contribution to the overall gradient of one particular point in our data. So we'll sort of look at the gradient at the rate at Wt minus 1, but only the contribution to that gradient given by one particular point. We'll call it x sub it, where this index I is uniform between chosen uniformly between 1 and n. Okay, so at each step I pick a random record and I use that to get an estimate of my gradient, just one record instead of the whole data set. So a priori, this seems like a kind of a weird thing, but if you stare at it for a second, you realize that this actually also gives you an unbiased estimator of the gradient. So on average, over the choice of records, the expectation of g tilde t is going to be once again equal to, well, let's do the calculation. It's going to be the average from I equals 1 to n of the gradient of L I would have seen for each of the points. Okay, because each point is equally likely to have been chosen. And just by the linearity of the gradient, this is equal to the gradient of the big loss function at that point, Wt minus 1. Again, for every sequence of queries that we might have made so far. So these are examples of this property of having the right expectation no matter what the previous sequence was. This is called being unbiased. So these are two examples of unbiased estimators, and they're probably the most commonly used. Just one note is that, in this stochastic gradient descent setting, there's nothing holy about choosing just one data point. You could choose a small batch. That's also often done. You can also use a small random batch. Okay. And what we're going to do is see how we might analyze gradient descent in this setting, in both of these settings. So let's, before we start talking about when these algorithms converge, because that's going to be sort of part 2 of the lecture, let's talk about when this, how we can set parameters so algorithms like this are differentially private. Okay, so let's look at the first idea, which we'll call private or noisy projected gradient descent, noisy PGD. Okay, so again, the idea is that, so just to be clear about what we're talking about, so for noisy PGD, what we're doing is we're modifying our basic gradient descent algorithm to use this noisy estimate. And then we're using that noisy estimate to do the update. Okay, so now that, of course, that means that our progress in optimizing the function may end up looking different. We could take, a pretty different step away from Wt minus 1. Or even, we could take a step in like entirely the wrong direction if the noise tells us to do that. And so what we'll need to argue when we come to argue convergence, we'll need to argue that the algorithm makes progress at each step, at least on average, even though some steps take us forward and some steps take us backwards. Okay, so this is the algorithm, and this is what we want to analyze. It has a new parameter, sigma squared, and this is what we want to think about. So the the reason this is differentially private is that even though the thing we're outputting is some sort of complicated function of the sequence that we've seen, so the thing we output is the average of the iterates we've seen over the course of the algorithm. We could imagine actually releasing all of the iterates to the adversary. Just think of the output as all of the WTs. And then just think of the final output W hat as some post-processing of those WTs. And if we think of the algorithm in that way, if we think of it as releasing all the intermediate values it computes, then really this is just an instance of the adaptive, the Gaussian noise mechanism with adaptively selected queries. The adaptivity here comes from the fact that the places where you make the you end up making the queries, the WTs where you make your queries, those depend on the noise that was added at the previous stages. Okay, so what can we say about privacy here? Well, turns out we don't need to assume much. So if L is decomposable, and as long as the individual loss function little l is is Lipschitz on C, on the set where we're exploring, so here this is Lipschitz. This means G Lipschitz in W for every possible X in the universe of acceptable inputs. Then noisy PGD is private, is epsilon delta dp, as long as sigma is sufficiently large. Okay, so when sigma is at least 2g over n times square root of 2t log 1 over delta divided by epsilon. Okay, so why is this? Well, we're going to imagine, as I said, releasing all the iterates. W0 all the way up to WT plus 1. And and now our algorithm, so we can apply, so each step of the algorithm, so if we release all these iterates, then this is just the adaptive, then this is a special case of the Gaussian mechanism with adaptive queries. And the overall sensitivity of the set of queries is always bounded. The overall sensitivity is so it's at most 2g over n, and this part I'll just write it out, times square root of t. So why is that? Well, this is the L2 sensitivity we're looking at, and if we look at the difference in, if we look at the gradient of L at some point with data set X minus the gradient of L at some point with data set X prime, each of those is a sum. Most of the terms cancel, and what's left is just one term two terms that are left over. So there's sort of whichever term that it differs between the two data sets, that's the term that's left when we do the subtraction. And so the norm of this thing is at most 2 over n times the maximum norm of the gradient, which is g by Lipschitzness. Okay, so now that we know the overall sensitivity, we can apply either the strong composition lemma from lecture 10, Or we can see there's a tighter analysis specifically for the Gaussian mechanism, which was spelled out in the in-class exercises for lecture 10. Okay, using generic strong composition is going to be a bit looser here, but it would give roughly the same qualitative behavior. And so what we get is that what matters is this sort of overall sensitivity. So if we look at like what showed up in this bound here, we've got the overall sensitivity times a factor of about square root of log 1 over delta divided by epsilon. Okay. So that's it. So the nice thing about projected noisy gradient descent is that it's the requirement, what you need for privacy is really very simple. And in fact, you don't even really need the loss function little l to be Lipschitz. All you need to do is just constrain the gradients to be not too big. So just a note, and this is what is often done in practice. We can enforce low sensitivity by clipping the gradients to a given length. G. So that clipping of the gradients might distort the function a bit, and might distort the process a little bit. But as long as you're not clipping too many of the gradients, then you're basically following the algorithm as we wrote it. Okay, so, but like for various complicated functions, like the loss functions that come up in deep learning, it's often hard to prove that things are going to be Lipschitz over the set you want. But that's okay. You can just enforce the condition. You'll definitely be differentially private. And then as long as your condition holds most of the time, as long as it doesn't distort the gradients most of the time, then you'll actually be doing something very close to just plain noisy gradient descent. Okay, so this is always private. It's basically got the same runtime as vanilla, the non-noisy projected gradient descent. And so this is actually pretty much the state of the art. Well, not quite the state of the art, but this is like a useful general purpose tool, and it's often where people start if they're trying to solve an optimization problem differentially private. Okay, so again, we're not going to analyze the convergence of this quite yet. We'll talk about that in part 2. Before we do that, I want to mention one extra idea which helps us get around this runtime bottleneck of the runtime bottleneck is something like t times n times d. Just that's what you need simply to manipulate the gradients, never mind to compute them, right? In fact, it's larger than that. The runtime is larger than that because the gradient computation itself can be expensive. But what we'll see is that, in fact, the same thing that people do non-privately to improve the runtime, which is the stochastic gradient descent idea, that also works here. Though it's a little trickier to analyze the privacy properties. Okay, so let's talk about that. Okay, so here SGD stands for stochastic gradient descent. And the idea is, in addition to adding noise, we'll also do this step of approximating the gradient as representing via the evaluation of the gradient on a small sample of points. And for today, I'll just focus on the special case where you're looking at one point at a time. Although you can also look at batches, and often that's a better idea. So again, so what will we do? So we'll do the same thing we did before. We'll compute some gradient now. We'll do We'll start out same way. We'll initialize to some random point. At each step, we'll pick a uniformly random index between 1 and n. And we'll calculate our gradient estimate as the gradient of the individual loss, the contribution by this 1 point x sub it, plus fresh random Gaussian noise in each component. Okay, and then we'll proceed with the algorithm as before. So ut is wt minus 1 minus eta times g tilde of t, and then we project. Okay, so that's we're taking the same template and just modifying this, how we get this this gradient estimate gt. All right, so now what difference has this made in running time? Well, now from what was t times n has basically become just order of t. So this is order of t gradient computations. Sorry, that's the time to compute gradient L, the gradient itself. And we still have these t projection steps potentially, which we just assumed we were going to work with sets where the projection was relatively easy. So that's that's a big win, right? We've just saved a factor of n in our runtime. Okay. Now, what about convergence? Well, it turns out that actually, if you set things up right in many settings, the convergence rate of this algorithm is actually pretty much the same as just vanilla noisy PGD, and even that is like sort of the same as pretty similar to what we get with regular non-noisy projected gradient descent. One of the reasons that this stochastic gradient descent idea has been so successful in practice is that it actually, when you're taking lots and lots of steps, it doesn't actually cost you that much in terms of accuracy. It adds some variability, and it definitely makes things more complicated to analyze, and to, there are complications that come up in practice. But it's sort of remarkable that it doesn't really cost you that much. Okay, so that's this is the basic idea of the algorithm. What about what happens when it comes to privacy? So what we did before with when we were just adding noise to the full gradient, we said, well, each step of the algorithm is a low sensitivity calculation. Like the L2 sensitivity of each step is about 2 over n times whatever the g, whatever the maximum length of a gradient is. But now, if we want to analyze this as a special case of adaptive Gaussian noise addition, then we need like a function at each step rather than this sort of like random process of picking a random index. And so that means that we'd have to think of releasing both the iterates and the indices at which we evaluate the gradient at each step. And that's going to cost us a lot. So to apply our adaptive Gaussian noise analysis, we would have to release both the iterates, the W's, WTs, and the indices at which we make our choices. Okay, and that's fine, except now all of a sudden the sensitivity of each step is much higher, potentially much higher. And even though any one point is unlikely to participate in many different steps, the cost to our sensitivity will increase linearly with the number of steps that a single point participates in. Okay, so our sensitivity will somehow be something like T over N times what it was before, right? 2G over, the sensitivity will be something like T over N times 2G instead, versus what it was before, which was like 2G square root of T over N. Okay, so if we think of these positions as the positions IT as being known to the adversary, then we're losing a factor of roughly square root of T in our sensitivity. So how do we deal with that? Well, it turns out that there's a fix. Okay, and the idea is, let's not use the adaptive Gaussian analysis. Let's use a different way to analyze it, where we don't actually think of the indices as being revealed to the adversary, but we rely on the fact that they're kept secret by the algorithm. Okay. And we're going to use their randomness in our analysis. So we're adding randomness to the process to gain efficiency. Why not take advantage of that to gain in our privacy analysis? And that's exactly what we can do. And what we get is actually a very general a very general transformation that allows us to take any differentially private algorithm that works on a small data set. And when we run it on a random subsample of a big data set, we actually get a huge reduction in the privacy cost. So this idea is called, this sort of general idea is called amplification of privacy by subsampling. Okay, so let's try and let me spell out like a version of this, a general version of this. So let's say A is an algorithm that it's differentially private, and it takes a single data record and outputs, something, whatever. And let's say this is epsilon delta differentially private. Okay, so just to be clear, it takes just one data record. Okay, so think of that as like the one data record that we're using to estimate our gradient at a given step. And now we'll consider a new algorithm, A prime, which takes a data set of size n and produces output in the same space. And it runs as follows. So on input n data records, it first picks a random index between 1 and n. And it then returns the value of the evaluation of A prime on this random record. Okay, so this is our new algorithm, A prime. And the theorem is that A prime, or the lemma, says that A prime is epsilon prime delta prime differentially private. For epsilon prime, here's the exact formula. It's the log of 1 plus e to the epsilon minus 1 over n. And you should think of that as roughly epsilon over n for small for when epsilon is, say, less than 1 or bounded by some constant. And delta prime is exactly delta over n. So this is a sort of a very general statement, and it applies to any differentially private algorithm, not just Gaussian noise. Just a moment. Okay, sorry, just fixing a technical glitch there. So this amplification by subsampling will apply to any differentially private algorithm, and it applies not just to subsamples of size 1. In fact, we can generalize this to subsamples of any size, so can generalize to samples, a subsample of a random subsample of size m less than or equal to n. And then our epsilon prime is something like epsilon times m over n, and our delta prime is exactly actually delta times m over n. And so this is the big benefit you get, okay, from subsampling. So that's a useful algorithmic idea. It's also sort of an interesting point to notice about privacy that kind of aligns with our intuition. Like if you imagine, the census runs a survey on some set of people that's like a small random sample from the bigger population. If the identities of the people who participate in that survey are not public, you would expect to get a much stronger privacy guarantee. And indeed, that's exactly what we see. Okay, but let's use this for understanding Gaussian noise analysis, Gaussian noise addition with DPSGD. So like, how does this help? Well, let's suppose that we add enough noise so that each step is differentially private kind of on its own. So let's say we're adding noise like 2g over epsilon times whatever we said before, 2d log, sorry, no t, sorry, 2 log 1 over delta. Okay, so let's just suppose we have this. Then each step, let's say this happens for some epsilon less than or equal to. So each step is epsilon delta dp when the index is known, when index it is known. And so by amplification, it's actually about epsilon over n dp when the index is secret. And then by strong composition, we can get that all t steps together are something like epsilon square root of t over n. Delta t over n dp. And thus we can actually get a much stronger guarantee. So this allows us to run like the algorithm for many steps, and for really big t, like let's say you set t about n squared, then in fact we get the same privacy guarantee, or same scaling of the privacy guarantee anyway, of epsilon prime delta prime, as if we had run the full gradient analysis. Okay, as we get the same privacy guarantee privacy analysis as if we'd run the algorithm which computes the full gradient at each step. Okay, so this subsampling idea really allows us to, in some sense, get like this efficiency almost for free. We get more or less the same privacy guarantee, at least in the right regime of parameters, and a much more efficient algorithm. So the last thing, before we move to part 2, the last thing I want to mention is that at this point we know various techniques to get a much tighter analysis than one can get via strong composition. And those techniques are sort of evolving. That's kind of a topic of ongoing current work in the literature, and those techniques are evolving pretty quickly, although I guess they've started to stabilize recently. Okay, so that's sort of the landscape of these private variations on gradient descent. And now what we're going to do in the second part is actually see how we can think about accuracy, at least in the relatively simple case where the function we want to optimize is convex and has, therefore has no local minima, only global ones.